I haven't been here before, so I don't know any of you, but I'm hoping that I hit the right level and that everyone learned at least one thing. I'm going to go through 4 examples, 2 common ones and 2 less common ones for tally tables and the apply operator in terms of getting data out of SQL databases. I've been a database programmer since 1990 and worked with all sorts of databases, financial databases, CAD/CAM databases, and if anyone bring your laptop if you want to, the presentation and the SQL code that the examples come from are all on that GitHub site. So we're going to go through tally tables first. What are they? They're a table of numbers, and they have various usages. They're also known as number tables, and they're closely related to day tables if you're in an accounting database. We're going to look at how to fill them and how not to fill them, and there'll be a performance example there. Their primary use is for filling gaps, and I'll talk more about exactly what that means. But another interesting use is indexing strings if you want to find patterns and do pattern matching, and it enables parallel computation, whereas a while loop would not. Then we're going to look at the apply operator, and in particular its use with the table value constructors that were available in SQL Server 2005, I believe. So we'll describe them, and then we're going to look at an unpivoting or folding example where we're taking data that's wide and making it narrow into a normalized presentation. And then we're going to look at how we can use them to eliminate case statements when we're doing the opposite process and pivoting them out. So, tally table is a fully indexed table of numbers, typically from 0 to n-1, and then you add it to some other data source in order to get the gaps filled. They're usually pre-filled to a well-known number of rows. A common number of rows is 11,000 because that comfortably covers all the days in a 30-year mortgage at daily interest rates. But you just fill them or create them on demand to whatever number of rows you need for the purpose at hand. They can be efficiently generated in a common table expression if not available as a static table. But beware of using a recursive common table expression because if you're generating a large number of rows, that can rapidly become horrendously slow. And I'm going to show you a slightly better way and a significantly better way. And they're used to replace loops. And here would be the schema definition for a typical tally table. I've created this one as a temporary table. So we're just calling it n, and again, I've got this. Type int, it's not null, and then we alter the table after we've filled it to add a primary key clustered index with a fill factor of 100. We're not going to do any inserts or deletes on this table, so we want it to be as compact on disk as possible so that we can get the best performance. So here's an example of how not to fill them. So we'll just go through the boilerplate code. So delete the table that's not there, create it. We're going to set a limit. As I said, 11,000 is sufficient for a 30-year mortgage, but for this performance test, we're going to multiply it by 10 and do 110,000 rows. So here's a little while loop. Everyone who's a programmer knows how to write a while loop, and it just goes through 110,001 times and inserts a row to the table. Then we add the clustered primary key, and then we see, oh, how long did this take? We took a start time here, filled the table, created the index, and lo and behold, this takes, and I ran this 5 or 6 times in quick succession to get it warmed up. So it starts at about 2.5 seconds and then quickly drops to about 1.8. You can see 110,001 rows. So 110,000 rows is not very much on a modern database, especially when they're just an int. It's half a meg, but it's still taking 2 seconds. So a much better way to fill them is this Ben-Gann tally table after Itzhak Ben-Gann, the well-known SQL programmer. And here what we're going to do is use 4 common table expressions. We fill this first one with 10 values. We do a cross join to generate a table with 100 rows, cross-join again to get 10,000, and cross-join again to get 100 million, potentially. But we don't actually need that many. We're going to select just our limit number of rows, which is 110,000, and we're going to add a 0 row to give us 110,000 plus 1, and then add our index, and this takes a quarter second, about 8 times faster. So that's basically 1.5 seconds of pure overhead that you're eliminating by using this construct instead of a loop. And that's good general advice for SQL in general. Avoid the loops, they're slow. I've had my wrist slapped a couple of times on Stack Overflow for this analogy, but the ratio is about right. Really, this runs as compiled code, whereas the while loop runs as interpreted. And the typical ratio is 8 to 10 times performance improvement when you can run compiled versus interpreted. Now, that's not strictly true, but we're seeing the same order of magnitude differences. So back to usage. The most common usage is to fill gaps. So in an accounting database, if you had a fiscal period table, which normally would, if it was fully normalized, would have a period number, the year, a fiscal period and the year number, and a begin date, but no end date, because now you've got inter-row relationships that you're typically trying to avoid. Sometimes you'll find an end date there, sometimes you'll have it, especially in newer databases, you'll see it being created on demand, especially using the leader lag function, as I'll show you in a second. So an example of how this helps is if you have a holiday table, you really want to keep this sparse. You just wanted a table of holiday dates for each jurisdiction. You don't want the holidays being swamped with the days that aren't holidays. But now you need to join to your data. So if you have your fiscal period table and a tally table and your holiday table, you can quickly generate a set of all the rows, all the days, and the holidays are flagged, and you can do your joins. So that's what we've just talked here, but there are other instances. Days table is not the only use. Another one would be if you're in a manufacturing environment, you're generating shifts, so you could fill in the hours. You could have a shift begin hour and generate the other hours if you needed to map things. And it also replaces looping with the while statement along the similar lines of the quick example we looked at in filling the table. And it's often more readable because of being more compact code. So the company that I was working for until January used 13-week periods ending on the 4th, 8th, and 13th, 17th, 21st, 26th week. So here we can go through quickly. So with the periods, we're getting, this is the period number in the year, the begin date, a pseudo date. This is always first of the month, even though the period doesn't begin there, but you can then use all your date functions in order to give whatever presentation for the date you want. You just operate on the pseudo date. It may or may not actually be in the period, but it looks to be when you do the conversion from calendar to fiscal. We're generating the end date here on the lead. Oh, yeah, that just shifted. So that's an important usage. The most common windowing functions are row number, lead, and lag. What this does, in this case, the lead is, it looks at the next row, or actually the first subsequent row in this case, pulls out the begin date, and it's ordering them by begin date. And then we get the date from parts. If we don't have a next row, it just takes the last day of the year. Then we generate the day count with a second common table expression, and then we can pull out all the days. And so here we have fiscal period number 4, beginning on the Sunday after the 13th Saturday, and ending on 17th to Saturday. So we're generating this. If you had holiday table, you just join it to this and you'd have the holidays pop up. So that's a fairly common usage. The less common one is to use it to index into strings and do pattern matching. So probably most of you know this old tongue twister. I learned it in grade 3, I think. And we're just going to take the length. We're going to do a sum of every instance from this test string, beginning at position n from our tally table, going to length that matches the pattern would or could, add them up, and we see that there's 8 instances of would and 4 instances of could in this little tongue twister. So anytime you're indexing into data, because this query makes clear that there's no row dependencies and no sequencing dependencies. So it knows that I can do all of these in parallel as fast as I want. You've informed the query engine of that, and so it can do that. So that's one of the possible ways that the query can improve its performance. And also, just because it's running against join, which the database engine is designed to do efficiently, as opposed to running in the while loop, which is use this when there's absolutely no other mechanism possible. And Jeff Moden, who's a well-known columnist for Microsoft SQL Server, has a string splitter. So this is pulling out comma-separated values that have been submitted to the engine. And he splits that on the commas and produces a row set of all the individual values in the string. This particular mechanism only works on strings up to 8K, which is the maximum size of a varchar or nvarchar before it becomes a text block. But that's quite efficient if you need to do string splitting on a delimiter. The apply operator, it's been in MS SQL since SQL Server 2005, comes in 2 flavors, cross apply and the outer apply. The outer apply resembles a left outer join with the join constraint specified in the where clause instead of an on clause. The cross apply similarly resembles a cross join. And you can generate an inner apply, I forgot to put the inner in quotes there, equivalent to the cross apply, but you simply add join constraints as in the outer apply in the where clause instead of an on clause. So you actually get all 3 flavors available. I'm not sure why they didn't put an on clause in, but really neither here nor there. So it works much like a join, but the additional capability is you can invoke a table valued function. So when you're doing a join, if you put a table constructor or a function, you can't reference columns in tables higher up. But with an apply, you can. And that was the original usage of the apply, was to allow inline table valued functions to be joined to where the parameters on the function call were column values. So you're doing a true join, rather than just in the on clause. But then in SQL Server 2008, we got these table value constructors. I'll show you exactly what that is in case anyone is not sure what I'm referring to. And this has vastly increased the power of cross and outer apply. And we'll go through examples of that. And in this case, it simplifies the folding and unpivoting of relations, and also can be used to eliminate case constructs. That's important because case constructs, especially if you have many of them on every row, you are potentially running into line cache flushes in your CPU, because in most cases you're writing those case statements where the branch predictor can't guess right, because half of them are going to succeed and half of them are going to fail, or 2/3 of them and 1/3. You're typically not really getting a high degree of distinction. So you can't guess accurately, and so you're flushing your line cache. If you can eliminate that and simply do a mathematical calculation, then you have the potential of making some sorts of queries run very much faster again. So here's a little example. Along the way, I picked up an accounting designation, so that's why you're seeing all these accounting examples. So typical manufacturing corporations often using activity-based costing. What that means is that their inventory records are broken down into categories such as direct materials, direct labor, direct service, and then the burden calculation of the indirect manufacturing costs, which is not to be confused with all the other stuff, the support departments. These are burdens that are actually generated. So these are the vice president manufacturing salary and his secretary's salary. None of that goes to individual jobs, but it all has to be burdened out to them. Anyway, you see two little lines here. So we've got the accounts receivable amount, the revenue amount, some tax amounts, the cost of goods sold, and then the cost of goods sold being balanced from a withdrawal from inventory. Typical denormalized, but for each specific journal in the system, this is not unusual. That would probably be the signature of a valid stored procedure that generated a credit sales journal entry. And you would send in some number of rows that were the detail lines of a credit sales journal entry, and they would look like this. But the actual journal table itself is going to be normalized, where all of these, you're going to add an additional accounting field and then have amounts. Either amount plus or minus, or positive amount with a debit credit flag, or maybe a debit amount and a credit amount. All three are common designs. So we need to normalize this. So here's the data so you can look at it. And here you can see the instance of the cross apply. This is the table of value constructor from this parenthesis down to here. And it's the same construct that was always available in insert statement, but now you can put it inside a join or a cross apply, and it's particularly useful in increasing the power of cross and outer apply. So in this case, we're simply taking all the accounts, and I've chosen to do a debit credit design here. We're just saying for each row, we want to create 3, 4, 5, 6, 9 rows with these account values, each one of which has one of these numeric values as the assigned debit or credit. And when we run that on our input data, we get this. We can see a nicely normalized structure. In this case, I've shown both the balance. You would not normally have both implementations, but I just put them here for illustrative purposes. The documentation numbers, the accounts. So that's nice normalized data. We can just simply do an insert, and if it's a single insert, it'll automatically be an auto commit transaction. Now the inner apply operator. So here's our data coming straight out of the normalized journal table. And what if we wanted to report out again in a pivoted format similar to our starting but summarized? So here we take our data, we're going to summarize it. We're just going to have the AR, the revenue, the 2 tax amounts, the cost of goods sold, and then the 4 inventory amounts. And this might be useful for a margin analysis. Here we use the cross apply again with our table value constructor. And notice the little grid into our output columns. And then we just do a sum. In this case, we need to do a join constraint, and because there's no on clause for the cross apply, we put it in our where clause. We join on the accounts so that each account row here is mapped correctly. And this is the output data. So again, repivoted again to a slightly summarized format. So that wraps up my little presentation. Hopefully everyone learned something new. We looked at a tally or number table, what they are, their relationship to day tables, in particular on the first example. We saw two ways of filling them and showed that one was running about 8 times faster than the other. Used them to fill gaps. Also useful for indexing into indexable data structures such as strings, which we did with that little pattern matching. And briefly mentioned a couple of windowing functions which have been introduced in SQL Server 2005. Then we looked at the apply operator, cross outer, and how you can generate an inner apply from the cross by simply adding a join criteria into the where clause. Showed a couple of examples of how to use them with table value constructors. Showed how they can be used as an alternative to pivot and unpivot. I never use these. I find them more typing and harder to read. And since I know I'm going to read my code 10 times as often as I write it, I always like to create code that's easy for me to read. And then I pointed out how they can eliminate the case operator with the consequent risk of cache line flushes, which is something you're not going to see necessarily as a performance hit, but may be a hidden performance hit that you won't detect until you actually do a comparison. Questions?
Are these operators available in SQL servers other than SQL Server? Like SQLite or Postgres or MariaDB or?
I know that they are in some,
okay.
but particularly which ones, I'm not sure. I have worked almost exclusively with Microsoft SQL Server through my entire career because no one will hire you as an experienced programmer for a database you haven't worked in. So I can't get Oracle jobs because, I'm willing to. It's silly, but it's life. So once you start becoming good at a particular database, as a database developer, nobody wants to look at you for another product. I know what Oracle will. Oracle definitely has.
Definitely? Okay.
Whether their MySQL product has them, I don't know, because that's a budget product, right? The other name brands, Postgres probably has them, I would think, but I can't say for sure. Anything else?
Is this compatible with MySQL? Or is the same question?
Well, the numbers table, because you're constructing it yourself, that'll always be applicable. You can use that anywhere. The apply operators, I'm not sure. You'd have to look in the documentation of your particular database to see whether they're available. It's also possible, there's no real reason that I can see where you would have to use the apply keyword instead of join. So it's possible the functionality would be added to another database, but they might just call it an enhanced join rather than calling it apply like Microsoft did. But you have to look in your own database documentation to be sure. I can't speak for sure about anything other than SQL Server.
Sounds like the operator is not available in MySQL, but you can certainly write something that's approximately equivalent.
Okay, I believe you. Any other questions? Yeah, come on in. Come on in.
I waited 3 times.
I'll just flip quickly back to the beginning. So the presentation and the SQL code is all available here on GitHub. And if you send me questions on GitHub, I will do my best to answer them within a reasonable time frame. Did everyone see something new? Good, okay, so I hit the right level. I was hoping that would be the case. Rita, over to you.
Okay, so thank you.